Coming people on Zoom, thanks for people coming in the room. Our speaker today is Charles Jenkins from the CSIRO, which is the Australian National Lab, and he's going to talk about a project that I adore. I hope you like this project. The Otway project in Australia is a CO2 storage experiment, and you know it's really fun for geologists and engineers to do an experiment like we do, like chemists and physicists get to do, where you really do something. So and Otway experiment, you'll hear from Charles about the details. Maybe you'll get to see why I think it's such a really strategically important, but also really fun experiment. Charles has been here with us for most of the summer as a visiting scholar and working here at the Bureau, and he's heading back to Australia. So we're really pleased to get him to come talk to you about this in the seminar series. He's an applied physicist with a PhD from the University of Cambridge. He's a fellow of the UK Institute of Physics and associate editor for the International Journal of Greenhouse Gas Control, which I shouldn't mention because he's probably going to send something for peer review next. But okay, Charles, we look forward to hearing this talk.
Thanks very much for that, Sue. It's been an absolute pleasure to be a visitor here at the Bureau for the last 3 months, and I do thank Sue for making it possible. It's been so stimulating. Sue's group is an inspiration to all of us around the world in the world of CCS. So it's been just great to be here. So my introductory slide here reminds me of the few occasions in my life I've had to make a speech at a wedding, and where you have to remember all the relatives. This list is by no means complete, because I'll be describing things that have been taking place since about 2004. An awful lot of people have been involved in the States and internationally, as well as from Australia. So we're not moving. Oh, there we go. Okay, so a few background words. So the idea of having a test site for geological storage in Australia is, if it's due to any one person, which, as I say, is probably not really a fair statement, but in this case, the person you have to name is Peter Cook, who some of you might know as a director of the British Geological Survey in the 1990s. And it was Peter whose maxim was that somebody had to come and kick the tires in Australia for a CO2 storage site. You had to be able to see it actually happening. And when this site was being designed, of course, the Norwegians had been doing storage in the North Sea for maybe a decade, perhaps less than that, but less than that. But it always makes a huge difference to do something like this in your own country. It makes such a difference to politicians at all levels. It means when you're at a barbecue and people ask you what you do for a living, and you describe it, and they say, well, you can't do that, and you can say, well, we did. And what's more, it's just down the road. So where is it? It's in the state of Victoria, which is down in the bottom southeast corner of Australia. And in the expanded map, you can see its relationship to the city of Melbourne. It's about a 5-hour drive from Melbourne. And as you can see in the aerial photograph, pleasant green, rather flat countryside, about 5 or 10 kilometers from the Great Southern Ocean, and a very popular tourist drive down the coast in that area. You can see cows standing in the fields in this picture, and that's because this is a dairy farming area. And from our perspective as operators on the surface, one of the things that probably won't surprise you if you've been listening to the news from Australia recently is that for about half the year you can't do any seismic on the site because it's too wet. And on the other half of the year, it's very difficult to run seismic because there's a total fire ban. But so this is just the way life is in Oz. Sorry. No, really. There we go. So here's a photograph of the site, and like all of you will be familiar from oil and gas operations, when you go there, there's really not very much to see. In this case, you see the puddles of water, which tells you which half of the year we were in, and there's a wellhead, and that's about it. we get lots and lots of visitors to the site, and really one of the things that we are showing them is, well, really there's almost nothing to see. So, as I mentioned, this project goes back quite a long way now, and I just wanted to give you an overview of the journey that we've been on and the different sorts of storage questions that we've tried to investigate. So some of the sort of background of funding and governance is of interest. So this site has been run by an entity called CO2CRC, which is a kind of umbrella organization for storage and capture research in Australia. It brings together businesses, industry, federal and state funding. And over the years, the money for this site, which is several $100 million probably now, has come primarily from federal and state governments. A lot of it has come from the Australian coal industry through a research levy that they pay. And the entity has many industrial members, much like Sue's Gulf Coast Carbon Centre. Big names like Total or Shell or Chevron are members, but lots of smaller entities as well who, for one reason or another, are interested in CCS and want to find out what it's all about and get an in on some of the knowledge that we're generating. So we began in 2004 with an experiment I'll describe briefly, which was the first one we did, which was to sequester 65,000 tons of CO2 in a depleted gas field on the site. And after that, we moved on to being more interested in saline aquifers, in other words, reservoirs that had not seen hydrocarbons at all. And we ran a number of small injections and two larger ones, 15,000 tons each, over the last decade. So I'll describe those briefly as we go along. One of the interesting things about this site, which makes it really very convenient, well, not just convenient, but possible to run a series of experiments like this, is that we don't have to pay for the CO2. When the site was bought, it contained a well which had been drilled for methane and turned out to be 80% CO2. This well's called Buttress, and we got this well as part of the package on the site. When somebody last looked, there was still 200,000 tons of CO2 down there, which at current prices, as you know, paradoxically, is an awful lot of money. So we don't have to worry about CO2, where it comes from. And in fact, even pumping it into the ground is relatively easy because the two aquifers are at almost the same pressure. So the pumping is almost like a siphon from one to the other. So that's something we kind of forget because it's a luxury we've just had for decades, but it does make a lot of things possible. So I'm not a geologist myself, but I felt obliged to put some geology in here for the benefit of all of you. So here's an image of the site looking down. This was produced around the time we were doing the very first experiment, the stage 1 experiment, and so it's focused on this well here, on this area here. This is the old gas field, and when we got the site, it had a well right into the crest of the structure called Naylor, which was going to be used for the experiment. So at that time, we only drilled one well, which is the injector here. We had the old extraction well as a monitor, and over here is the CO2 well, which I mentioned. And the scale of this thing you see down here is about 1 kilometer, so this is all quite compact. Here's a cross-section along that line, that vertical line you see in this diagram. And there's an impressionistic geological cross-section, and the things that sticks out to you, even if you're not a geologist like I'm not, is that there's an awful lot of faults here, and everything is broken up into quite small blocks. We were interested for the first experiment in this old gas reservoir down here, which the Naylor well went into, and a bit later on, we'll come on to this overlying saline aquifer, the Parati, which is the one where we've done most of the recent experiments. So the stage 1 experiment had kind of everybody and his brother come along. It did all sorts of things because it was the first one. From the point of view of storage, it was kind of the safest thing you could have done because you were putting CO2 into this reservoir that had methane in it for millions of years. It had a convincing seal, and a lot of what was done in the experiment was to first of all make the point that it could be done. Something very important it did was to generate the necessary regulations to do the experiment. when this all began, no one had ever thought of putting CO2 in the ground in Australia. And so there were no regulations to say how you could do it. There was no legislation whatsoever. And it's one of the kind of unsung stories of getting the whole thing started, was the efforts of senior people like Peter and many others to actually engineer the creation of the necessary legislation. And as you all know, getting acts of parliament in Australia or anywhere else made is not an easy thing to do. And getting all of that in place and finding out who was responsible for overseeing those regulations, who you had to report to, all this kind of thing that it's easy to say, had to be worked out completely afresh. And all of that work in governance has stood us in good stead over the remaining 2 decades, because we haven't had to do any of it again. We have a framework for operating in. Scientifically, the concept of the injection was quite simple. You see over here in the CRC1 injector, the well we drilled, we push the CO2 in down dip, and it floats up dip under buoyancy, and it arrives at Naylor, where all sorts of monitoring equipment had been placed to get the progress of the CO2 gradually filling up this container. So there was a packer, which you see here in this picture. Below it, there was some U-tubes, which came from LNBL, from Barry Freifeld and his group. And there was a whole bunch of other sorts of electronic hardware and jewelry down there to monitor the progress of the CO2 coming up in the reservoir. So the first thing we discovered was that nothing ever works properly downhole, and we lost contact with everything below the packer except the U-tubes, which thank goodness kept on working. But all of the seismic gear and geophones and stuff that was down there, we lost. So much of the reservoir monitoring in this experiment came about from monitoring traces, from essentially geochemical analysis of samples that were picked up in those U-tubes. So samples are brought to the surface under pressure and taken away and analyzed, partly for traces. The top one is SF6 that was put in the injection stream, and also just for CO2. So this was most of the data that we had from this experiment on the containment aspect and how things behaved in the reservoir. It proved impossible to get any seismic imaging because there was already methane in there, and so you couldn't really tell the addition of the CO2 because the methane dominated the reflections anyway. So the top graph, the color coding shows the variety of predictions that we had for various statistical realizations of what the reservoir might look like. And as you know, there's usually quite a large spread in things like arrival times for traces. So that's what those various models of the various light green shaded areas, showing the concentration as a function of time, and then the observations are the orange dots. And obviously quite a lot of scatter there, but really it's fairly clear that we came in right at the beginning of the range of predictions. And the CO2 below in the bottom graph shows that pretty clearly as well, and rather less spread there in the predictions of the traces. So these data told us that the CO2 had gone into the reservoir, that it arrived. It gave us some idea of the volumetrics. And a useful thing we could do, because we had 3 U-tubes at different levels, is that we could measure the rate at which we could fill this reservoir, which was useful information since it already had water and methane in it, residual methane. And so it was a useful way in working out what the capacity would probably be for such storage, really, but in any circumstances where you had residual methane, and there's a lot of storage around the world like that. And because this was more than 10 years ago, it seemed exciting to us that you could put so much CO2 into depleted gas fields. Of course, since then, almost nobody has done this or anything else very much, really, unfortunately. One of the areas where there was a lot of work done in this early stage was in monitoring near the surface. This I think was at the time was still fairly new territory for all of us, and we hadn't quite worked out, to put it bluntly, what we were going to do with all these data. Because this was a first experiment and there was a lot of money sloshing around for everybody, we did all sorts of things at the surface. Probably the most important one from the point of view of the social license on the site is in the little picture down at the bottom there, which was we measured the water composition in the farmers' well bores all over the place, all over the site. The farmers draw their water from the shallow limestone aquifer at the surface, but there are a number of deep strategic reserve aquifers as well that we also monitor. So a lot of data was collected, first of all baseline data, and then monitoring data over almost 10 years of the condition of these aquifers. Another one that we did a lot of, which this was before Catherine explained to us how to interpret the data, so we just collected lots of it and puzzled over it, was soil gas data. This was collected over a very large, well, to us, a large grid, about 1 kilometre on a square, which you can see the little map there. And the person in the picture is one of the many generations of reluctant graduate students who had to go out in the heat of the summer and collect these samples. These, of course, were very puzzling to us because most of us were geophysicists or physicists, and we hadn't really thought about how we'd interpret these data. And of course, what you find out, as Catherine, I'm sure, has told you folks, is that the CO2 measurements in these data are all over the place. They vary with season, they vary over the years. Some of them are 10%, some of them are 0. It was very, very difficult data to interpret, and difficult to explain when you're trying to build up social license. One of the other ones that we did, which has now faded from view mostly on the international scene, was just measuring CO2 in the air. My colleagues at CSIRO have been experts in all sorts of atmospheric compositional measurements to very, very exquisite levels of sensitivity, and that's them going up their tower where the air composition was measured downwind of the injection well for several years. And again, very difficult measurements to interpret because the CO2 levels in the air are changing all the time, and trying to figure out what the signal would be if one had any sort of leakage is quite challenging. Just as an example of that, one of the highest CO2 readings we ever got with this equipment was one very still night when there was a small bushfire nearby, and the CO2 levels went up to about 1,000 ppm without any leakage. So we learned a great deal from collecting these data and understanding how to interpret them, and I think over the years we've realized that these type of data are not there to monitor anything geophysical. They're there as assurance for the local landholders. To be fair, this was recognized at the time, but trying to cope with the resulting flood of data and maintain the line on this sort of interpretation was something that we really had to learn, I think, both nationally and internationally as we went on. So that was stage one. That was 65,000 tons, and I guess it gave us that good experience of surface monitoring, gave us a lot of confidence that we understood storage under relatively simple circumstances. Certainly not the first time this type of thing had been done, but as I say, the first time it had been done in Australia with all the concomitant administrative and regulatory things that we had to get in place. So the next step was to move up into the Parati, which you see in this little sketch here. So this is a classic heterogeneous saline aquifer. It's very flat. It's not got any really clear structural closure of any kind, and it would seem to us to be a good model of the kind of saline aquifer that was being talked about as where one would find an awful lot of storage nationally and internationally. So the overarching idea here was, well, we don't have a structural closure here. We're not going to have buoyancy doing an awful lot for us. It's not going to be a simple kind of just fill up a container kind of storage. So we need to characterize what's going on in this aquifer pretty well. And then we're going to do an experiment where we put in CO2. We're going to see if we can detect it seismically, which would have been the first time for us at relatively small amounts. And we're going to see when we turn off the injection whether the propagation of the plume actually stabilizes in these circumstances, because there's nothing very much making it go in any one particular direction. So, as was well known at the time, one of the primary trapping mechanisms in these type, well, in any sort of aquifer really, is going to be capillary forces, and this happens because the CO2 wants to curl itself up into a little ball as water goes past it after the injection. There's a nice animation of this here. If I go back, will I be able to get it to work? Yes. No? Okay.
The thing to press was at the bottom left.
Was it?
Yeah.
Ah, yes. Thank you, Catherine.
Can I have a second?
Yeah.
Oh. Media is not found, so maybe it's not come from.
Oh, okay.
Is the file still on your side?
Okay, let's just leave it. I think the concept is probably familiar to most of you. That the reason for wanting to check this is that the immobilization mechanisms which would have stabilized our gas in our aquifer are really twofold. One is simple dissolution of the CO2 in the surrounding brine. That's quite an important mechanism and surprisingly quick. And the other one is this capillary trapping mechanism, which is responsible for residual oil, which I'm sure everyone in the audience is familiar with. So our first step was to do an experiment where we tested the magnitude of the residual trapping in this particular aquifer. And while it obviously at kilometer scales in the case of residual oil, this is well known, and it had also been experimented on a lot on the core scale. What we wanted to do was to see if it actually happened on the mesoscale, on the scale of tens of meters, and it happened with CO2, and it happened in our aquifer. So this ended up being a fairly elaborate experiment, again, based around tracers, quite small injections, 100 tons of CO2 that were put in, chased with water to get you to residual trapping, and then produced back to look for the signs of tracers. And chromatographic methods allowed us to get estimates of the residual trapping and characterize the reservoir. So based on that, we were able to design the experiment and have a better idea of what to expect. And as I mentioned, an objective here was to see the smallest amount of CO2 possible that came into the aquifer, to see it by seismic methods. The reason for doing this wasn't just curiosity about our seismic equipment, but it goes back to an idea that Sue and her group have advocated for quite a number of years now, which is that you can use an overlying aquifer over CO2 storage as a kind of sentinel. And if CO2 gets into it, you should be able to see very small amounts. So it's the canary in the coal mine principle, sometimes called an ASME, an above zone monitoring interval. So in this case, we were going to simulate a leakage into one of those cavities by putting CO2 into this Parati saline aquifer and see the smallest amount that we could see. Well, there was some very exhaustive characterization of the noise properties of the site done by our colleagues at Curtin University in Perth, and they reached the conclusion, not completely surprising to those of you who know about seismic work, that the best thing to do would be to bury the geophones at about 2 meters depth to get away from all the surface noise, which is considerable even in a quiet-looking place like this. And although it looks like a lot of work to bury an array like this, it actually saves a lot of work too, because when you're doing a whole bunch of repeated surveys, you don't have to come and lay out all the geophones, especially across all the farmers' fences and negotiate with all the cows and all that kind of thing. It's all just sitting there, and really the only thing you have to do, which is not negligible, is organize running your vibrosize along the surface. So there's just some pictures of a seismic array in progress, and the map shows you that we were setting out this buried array across about a square kilometer. So all of this work ended up with what I sometimes refer to as one of the shortest movies in history. So we got a 5-frame movie of the evolution of this plume, and here are the images again around a kilometer or so on the side, and the really important ones, I guess, for me are the first and the last. It proved possible to see the CO2 plume when there was about 5,000 tons in the aquifer. So that's really not very much at all. That's completely inconsequential from the point of view of any environmental impact. And it tells you that indeed with this layout, you've got a really good chance of doing this kind of sentinel arrangement and seeing a small injection seeping into any overlying aquifer if there should be any sort of leakage. The other one that is of interest really is the last few, which span about 2 years. Particularly, there's nearly 2 years between these two, and what they show you is that the plume stabilized. We've searched around quite a while for what word we should use to describe what seemed to happen, but stabilized seemed to be a good description. That basically the CO2 went in there, and pretty soon dissolutions and capillary forces stopped it going anywhere and just chewed away at its edges. And in fact, nowadays, nearly 10 years later, it's in fact quite obviously even smaller than this, mostly because it's about a third of it is dissolved. So that was the second stage, and that was another 15,000 tons from our inventory. After that, we had a bit of a pause to kind of figure out, well, what do we need to do next? And our conviction was by that stage that we knew saline aquifers were going to have to be a big deal for storage internationally. That's where the capacity was. And it was also, I think, becoming clear that we were going to have to use geological formations about which not very much was known, because we were going to want to stay away from places where there'd been a lot of hydrocarbon exploration because of abandoned and legacy wells. Now, this is not a black and white issue, but certainly it does prompt you towards looking for somewhat unconventional forms of storage compared to using old hydrocarbon reservoirs. So that points you towards the question of monitoring. If you're going to be using, I don't want to say unknown, but less familiar types of storage than if you were just going back to an old hydrocarbon reservoir, we think we're going to need some monitoring methods which we can focus on particular areas of risk rather than monitoring the whole thing. And it had also become pretty clear to us that we wanted monitoring that you didn't have to do much. You didn't have to be on the surface very much, because even for us, operating essentially in farmland and with very good relations with the neighbours, coming and doing monitoring on the surface is always a big deal. It's always difficult. At the minimum, you have to send people, which is always complicated and expensive, and then you have to negotiate access. Something always goes wrong. There's always the risk that you're going to cause some trouble for the neighbours, which you don't want. And just as importantly as that, really, it became very clear to us, and it's not exactly news, that the deeper you could get, the closer you could get to the CO2, the more sensitive you would be and the more focused you could be on the particular issues that you wanted to measure. So we had two ways of doing this in mind. They all involved drilling quite a number of extra wells, and we were fortunate to have obtained very substantial funding from a federal CCS program that enabled us to contemplate this. In the sketch is our concept of how we were going to develop the monitoring in the subsurface idea. So again, this little sketch is the scale here across is around a kilometer or so, and the idea was to inject the CO2 over here. At the first well we drilled, CRC3, there's a very gentle slope to the formation that allows us to float the CO2 upwards. And the idea was that we were going to make two pairs of gates. And this was going to model a circumstance where you might be injecting at a large saline aquifer, relying on long migration lengths through the aquifer, and gradual residual trapping into solution to stop things, to slow things down. And so you may wish to examine that process at particular places and times. And so these gates were intended, were models of that concept. In practice, the layout wasn't as clean as that. Here are well 6 and 7 over here on this side. We were able to make a gate. over on this side, it happens that there's a very large fault that runs approximately along here at the reservoir level. And on that sketch of yours, we would have put this well number 5 on the far side of the fault. And we agonized over this for ages because although that wouldn't have been a problem for any seismic methods, we had no idea whether this fault was sealing to pressure or not. And since some of our methods were pressure-based, we were afraid that we would get the well 5 on the far side of the fault and not be able to see anything because we were isolated from the injection reservoir. So in the end, we had to compromise and put well 5 over here somewhere else. So something else I'll just indicate while I've got the map up is that, as I mentioned, one of our concepts was to use downhole pressure measurements to measure the progress of this plume that we're injecting over here. But as I'll come to in a moment, we were also going to be doing seismic measurements. And a number of permanent seismic sources, which I'll come to in a moment, were installed, dotted around the site here. These are these yellow dots. These are so-called surface optical vibrators designed at LNBL, and they provide permanent seismic sources, which is very convenient. So coming on to the seismicity first, the seismic measurements first of all. So the new development here was, instead of using geophones on the surface, we decided to run fibers actually on the outside of the casing of these wells. These are the so-called distributed acoustic sensors that many of you know about, where the fibers are sensitive to acoustic waves. And because they cemented to the casing all the way down the well, you've effectively got a geophone string with a spacing of just a few meters top to bottom in the well. And because it's really quiet down there, they're exquisitely sensitive as well. And you can just get continuous data out of them. You can get a terabyte a day if you really want to. Running these fibers on casing is not free of risk, obviously, because the fibers clamp to the casing. When you're running the casing in the well, you haven't got your usual option of rotating the casing to try and get past any tight spots. And you don't want to reciprocate it all that much either. So really, when you do this, it's a matter of just running the casing straight in and hoping that nothing happens. And watching it happen is fairly tense, as I'm sure those of you who have been on field operations can remember. The other tricky bit is, of course, perforating the well once you've got everything in place, because you don't particularly want to perforate the fibers. And so you have to use orientatable perforation guns. And you have to have markers on the casing to tell you where the fiber is at your perforation depth. So not exactly rocket science, but certainly not commonplace and somewhat risky. But nonetheless, we were able to get fibers in all of the new wells we drilled on the casing. And additionally, we ran fibers actually in the well bore, in some cases on tubing and in some cases on cable, to mimic the situation where you might come back to a well and want to put fiber in it. So we wanted to see what would happen if you had to have the fibers sitting essentially in the brine in the well rather than in contact with the formation. And the way these were used was essentially to make vertical seismic profiles, VSPs. We had permanent sources, which are these green dots in this image, and you just shoot into the fibers all the way up and down the wells, and that enables you to make a real movie where you can get an image almost every 2 days for as long as you like. And over here, for example, where the reflection points are, this might be where you're seeing the plume emerging from an injection well, or here might be a point where you just have an area that you think is perhaps of some risk, and you can just monitor it all the time by suitable placement of your source and your monitoring well. The seismic sources themselves are these green objects here. There are 2 of them, one for low frequency, one for high frequency. Very small footprint. Really all you need is this concrete pad and 3-phase power. One of the beauties of these sources is that they are very, very simple in their design, so they can be maintained at a relatively remote country location without too much of a hassle. they're not a lot more complicated than washing machines. And our site operator from time to time pops down to the nearby town into the equivalent of Home Depot and gets spare parts for them to keep them going. So they're just perfect. And we don't run them during the day, just in case they annoy anybody, during the night, I should say, in case they annoy anybody. But it takes about 2 days to get an image with one of these sources shooting into the fibers. Something I might just mention at this point is that although the wells were drilled and commissioned, the actual injection phase of this project had to happen during the pandemic, and it happened at a stage when movement in Australia was extremely limited. State borders were closed unpredictably much of the time, and quite apart from that, the locals at this area where we work had made it very clear to us that they really didn't want visitors. The local hospital has one ventilator in it, and so we just didn't go there for about 9 months, I think. And as I mentioned, we have one site operator, and in a kind of miracle, really, our geophysics colleagues at Perth managed to get this entire system operated remotely from Perth with the assistance of one site operator, I think mostly by putting things in the post and putting them together over Zoom. But in the end, we were able to run these surveys remotely. As I mentioned, they produce around 1 terabyte of data every couple of days. All of those data were squashed down to manageable volumes on site by working remotely from Perth. And in the end, the results were just kind of emailed back, containing the latest seismic image. So that was something we hadn't expected, obviously, but it was a great advance to be able to run our monitoring with so little site presence and be able to do so much remotely. That was a great learning experience. Just another shot of the SOVs and some of the cows. And here's the type of answer one gets. So a somewhat complex diagram. I'll just step through it for you. So again, a scale bar. Here's 700 meters. And here are 2 of the monitoring wells I mentioned. There's the injection well, and there are the other 2 monitoring wells. And down here are these permanent seismic sources. And each of these lines here represents the reflection points where the rays from one of these sources hits the reservoir of interest and bounces back into the acoustic sensors. So during routine operation, you're obtaining information about essentially the impedance all along these lines. They've been put where they are because they're traversing the plume that we've made. And so they're giving you information about its progress as it gradually develops. So over here is the plume that we made eventually. This is as it looked about a year ago. This is an outline from an ordinary surface seismic survey. And you can see that all these traverses have been arranged to monitor this plume as it gradually progresses in this updip direction here. Over here, the yellow outline. This is the plume, the seismic plume, the CO2 plume that we'd made in the earlier stages in the stage 2 injection. This is the one that's just sitting there, gradually getting smaller and smaller that I mentioned to you, and it's also being monitored because our modeling suggested to us that these 2 plumes are going to interfere with each other. They're in the same reservoir, and this one might start to move again. So a number of the monitors have been put to monitor this plume as well as this one, which is the new one. So what actually happened is that those VSPs, those measurements every 2 days, as the color coding here shows, picked up the creation of this plume and the new plume and its gradual propagation up dip. But interestingly, at a late stage of the injection, they also picked up the 2 plumes merging with each other, and some indications that the entirety of this plume, this old plume, has started to move a little bit when the new gas arrived and started pushing into it. The most convincing evidence on these measurements is here. What this transect here is telling you that there's certainly something changing in the old plume, and the same over here. But interestingly, it didn't do very much. You can pick up very small changes with these sensors, but there wasn't much sign of anything more than what I'm showing in this diagram. Certainly the old plume didn't just pick itself up and run away. So I mentioned that we were interested in pressure monitoring as well. Downhole pressure, of course, has been used in oil field operations for a very long time. It's very informative. What we tried to do in this experiment was to develop a variant of the classical interference test, where we would inject water at one of the monitoring wells and measure the pressure response of the others. And it turns out that you can invert those measurements to get information about the distribution of compressible fluids in between the wells. It's a somewhat complex inversion process, but it can be done. Here's the pressure time series over the period that we did the injection. I've just included this to show you how the water injections happened. So these are pressure measurements at all of the wells listed down here. So here in December 2020, before we started, this was a baseline injection where we hadn't put our CO2 in the ground yet, and we did water injections at all the wells and found out how the pressure responded. So that was a baseline. Then we have the complicated real-life series of trying to get the compressor started, putting CO2 in the ground, compressor failure, power outage, all the kind of stuff that happens in the real world. By the end of this whole performance, we had a little over 5,000 tons in the ground, turned everything off, did another series of water injections over here, started again, everything went a lot smoother, got about 10,000 tons in the ground, did another water injection, and so on. And from this, it was possible to invert these pressure data to get a kind of crude image of where the CO2 had got to in between the wells. So over here, just as an example, I've shown the kind of recording that you get of the pressure in one of the wells while you're doing these water injections of the other wells. As you would expect, you get a whole series of pressure rises and fall-offs. The amplitude is pretty small, it's under a PSI, but the environmental noise is a lot smaller than that, and so you can rely on these measurements and fit models to them. And when you do that, you get images of saturation. Over here is an example. So there's the plume that we put in, and there's the old legacy plume. This is quite late in the injections, and the pressure tomography method is indicating that it's seeing CO2 in approximately this kind of area, and indeed, probably the strongest signal it's getting is from the front end of the legacy plume, indicating that interference with the new CO2 that I mentioned before, and also some indication of something happening way down at the bottom here, the far end of the legacy plume. Since this diagram was prepared, we've also done full-scale uncertainty analysis on these images. So this is kind of just this image has no error bars on it, obviously, but we're also able to make 50% probability contours, which of course are somewhat bigger than I'm showing here, but give you a better idea about what to believe and not to believe from the pressure tomography. But our concept for this is that it's the kind of thing that you can do relatively easy, and you could use it as a warning system. It's not intended to make a detailed map, but it's certainly true from the uncertainty analysis that small amounts of CO2 have a big effect on the compressibility, and you can get a good idea of approximately where something is changing, and then you would turn on more elaborate forms of monitoring. So I'll just wind up by mentioning that we did a whole bunch of other things as well, which I don't really have time to go into. We simulated above zone monitoring intervals again during the period that before we had CO2 in the ground. We could use those water injections as test pressure pulses and see if we could locate them with all the other pressure sensors, locate them where they are in space. That worked pretty well. We have lots of data on earth tides, which we're still trying to interpret. There's an awful lot of information in earth tides. Distant earthquakes turn out to be very useful seismic sources and give us quite a lot of diagnostic information about what CO2 is doing near the wells. And passive seismic, we've got loads and loads of data which we're still working on. I just can't resist showing you this earth tides, this pressure log of earth tides, because it's just such exquisite data. This is the pressure measured downhole, and the amplitude of this scale here is in pounds per square inch. So it's a tiny, tiny signal which is beautifully recorded by the gauges. These characteristic double-peaked humps all over the place are just the 2 tides a day in the earth tides. And the slow oscillation here is the changes in barometric pressure as weather fronts come past. There's a huge amount of information locked up here about the compressibility of the rocks in the vicinity of the gauges, which we're still working on. So the stage 3 conclusions for us was that we'd managed to make methods of monitoring which were pretty unintrusive on the site, which could be run remotely, which are very sensitive. So that was really the takeaway from the 3rd stage of our work. So looking back over 2 decades, storage, it was extremely important to prompt development of legislation and regulation, a pretty boring sort of thing to think about, but really vital work that gave us the ability to run experiments in a continuing way over the next 2 decades, and which made it possible for more wide-ranging legislation to be developed that covers CCS in Australia now in all the states and territories. We developed a lot of monitoring methods, and I think it's important that we discarded a lot of them. We don't want to run a physics experiment here. We want to do garbage disposal in the safest way possible. Quite substantial, I think, is the way confidence grew, both within the team and also more widely, as the geology was better understood at the site and things just happened the way they were supposed to. And that confidence floats out through the membership into all sorts of, in all the membership companies, which is important. We developed a lot of human capital, and importantly, CCS has not gone away from the public debate. We have lots and lots of visitors. We did it, anyone can come and look, which I think is important. So with that, I'll close and take any questions.
How do you want to do? All right, we'll do question in the room. We'll take turns. Question in the room, question online. Catherine?
Thanks, Charles. That's a great presentation. I'm wondering, so the first injection you did was in a depleted gas field, and right now there's a lot of discussion about some of the challenges of injecting into depleted gas fields. Did you come across any of those challenges yourself, or and what was that like for you doing that first off?
Yes, what you're referring to is the very rapid cooling that can happen with gas going into a very under-pressured field. Ours was not that under pressured, so we didn't have to confront that. There's a very strong aquifer drive. So these recent concerns were news to us as well. It was not something we'd seen any sign of.
Probably lucky if that was your first go.
Yes. Yeah, there were some other problems. Yeah.
We have some questions online. Anybody's read them? More questions in the room?
And Hong Lu Zhang, I'm a geophysicist, and I have a question about your 3rd stage test that shows the boundary of those CO2 expansion. What's the seismic parameter or attribute you use to make that?
So you're asking what the contour is of?
Yeah, right.
Yeah, I believe that's saturation times height. So it's an estimate of the, yeah. So really it's sensitive to the saturation of CO2 in the rocks. Yeah.
Let's take an online question. James, do you want to unmute and ask, or you want me to read it? Did you,
You could read it, that's fine.
did you measure land surface inflation and any detection of induced seismicity?
Okay, so two questions there. Land surface inflation, we certainly considered. The volumes were calculated to be too small for the effect to be readily detectable. We did try using a test with INSAR where we got some permanent reflectors and dotted them around the site. What we found was that the land surface moves an awful lot because of seasonal effects, because of the water table. And that was really all we could see. And that was a lot bigger than any predicted geomechanical effect. Induced seismicity, yes, there are small seismic events, very small seismic events in the reservoir. They've become easier to see now. We've got the distributed acoustic sensors. They may contain useful physical information, but we haven't managed to unravel that yet.
Another one online from Ronnie. Two questions. Any plan to take fluid samples and or even core after to see if there's any impact to mineralogy after injecting CO2 into the saline zone? Is there, and second question, is there expectation to see the CO2 floats on top to the top of the reservoir and preferentially spreads out from a top layer first when injecting in saline zone?
Just to take the second point first, yes, so that's certainly what happened. The plume is pretty thin. It's gone up against the top baffle in the reservoir and spread out in a very thin layer quite a long way. And that what was of interest to us was whether it would stop or not, which it did. The first question about samples is that we had thought of putting U-tubes in one of the wells, but basically we ran out of money, or we could see we were going to run out of money. And so we unfortunately weren't able to do that. There is a plan, a gleam in someone's eye to have a stage 4, which will involve drilling a well through this plume that we've made and collecting lots of core from that, which would certainly be of considerable interest for the geochemistry and mineralogy. Yes.
Linda.
Thank you. Thank you. That was, Sue was right. This was a very cool experiment. I really appreciate your sharing this with us. I am curious about your communication with the public. You mentioned several times that there were concerns, and could you share what type of concerns they had and how you were able to communicate with them to help them get over that?
Yeah, so the context is important. So this is a farming area, so it's not very densely populated. So in the number of neighbors you have to deal with is relatively small. And as regards that particularly, the operating organization, the CO2CRC that I've mentioned, from the very beginning has run its public relations program on the very simple principle that you heard it here first. So whatever it is that happens at the site, whatever people may read about in the newspapers, we try to make sure that they hear it from us first. We have in addition to our site operator, there's a community liaison officer who is resident at the site, in the area. Over the years, this has always been somebody who knows the community, a retired school teacher, someone like that. And there are regular community forums. Before anything big happens at the site, there's always lots of information handed out, and visits are made. The liaison officer actually goes and sees people and talks to them. So that's the way the local part of it works. And I think because of that, there's never really been any controversy that's leaked out of the site into the wider area. It all just works. Nobody makes a fuss about it. It's not very interesting to go and look at. And so the higher level public relations around the injection has almost all been kind of under our control, in the sense that we decide that we want to tell people, put out press releases to say we've done things. we don't, very rarely do we have to respond to criticisms or scandals. Yeah.
Okay, we got two more. Let's see if we can jam them in. From Mosen, can you share more detail about the results from your ASME campaign?
I was wondering if that actually, sorry for chiming in, I was wondering if that corroborated any of your geophysical data and your pressure inversion that you had done. Sorry for not being clear in the question. Thank you.
Okay, so I'll say a little bit more about the ASME. I might just go back to the image, actually. So the concept is, just to reiterate, is fairly simple, which is that you have this overlying aquifer. You get a leak of CO2 into it. It puts up the pressure at a point. That pressure wave propagates through the aquifer and it reaches different gauges at different times. That's the simple picture. We did this in this diagram that I'm showing here. We injected water at this green well here, and we measured the pressure pulses at these other wells, and then essentially just worked backwards to where it must, you get a distance from each of those wells, right? And where all those distances intersect, which is where all these circles intersect, that's approximately where the source should have been. And indeed, the method came very close to the source of the pressure. So that was a very simple pressure inversion, assuming a homogeneous aquifer. We pretty soon found out that if the aquifer is complicated, this process doesn't work very well. For example, once we had a tiny bit of CO2 in there in the reservoir, this type of inversion just doesn't work because the travel times of the pressure wave are too different so different in the CO2 than they are in the brine. But for the kind of ASME monitoring that Sue and her group have talked about, one would have a virgin aquifer with no CO2 in it sitting above the injection zone, and as long as it's reasonably homogeneous and doesn't have faults and barriers in it, this kind of simple inversion should work to tell you there is a pressure pulse and it's coming from approximately over here.
Okay, last question. From a regulatory perspective, do you see a subsurface plume conflict, one plume impinging on another plume, as a concern at this point? Or any thoughts on how to manage or mitigate such a conflict?
Yeah, I mean, we were interested. We collided these two plumes deliberately because one could. I mean, certainly in the oil field, you get lots of different people operating in the same reservoir or in stacked reservoirs, and it seemed worth just trying and seeing what would happen. We were fairly confident that nothing much would happen, and although we can see seismic changes, the plume does not appear to have moved. At all. I would imagine, and for us from a regulatory point of view, all of this was covered off with our regulators, and the risks were thought to be manageable or probably not really present. I imagine one would have to negotiate these things case by case. You can imagine lots of different circumstances. For us, it was clear that even if the legacy plume did move, there was kind of nowhere for it to go. There was nothing consequential that had posed any risk if it moved a bit. That could be quite different in other circumstances. And in fact, in the Australian CCS regulation, one of the biggest concerns is interference with other people's operations. I mean, here in the States, the concern is very much with groundwater. And interestingly, in Australia, the groundwater is not talked about very much. It's interfering with other people's oil and gas operations that the regulations are really worried about. And this would be a clear case in point in that. It may yet turn out to be a useful example if that's ever has to be discussed by way of changing that regulation.
Okay, thank you, audience in the room and online, so much for your participation. Thank you very much, Charles, for being here. Can we have a round of applause? And if you want to catch Charles, he's around with us for one more day. So catch him today before he zooms off back to Australia. So thanks, everybody.
Thank you, Sue.